Swayam Prabha, Digital India, Educated India.
Tutorial number 3. In this tutorial, we will be looking at problems related to Lagrangian mechanics. So most of these problems you would have studied when you are doing Newtonian mechanics, but here we will approach the same problems by constructing Lagrangian. Usually the Lagrangian is written as L. It's a function which is usually written as t minus v, and using the Euler-Lagrange equation, we'll rederive equations of motion, and in many cases we will see that using the Lagrangian formulation is much faster to much more efficient to arrive at the equations of motion, which you can also arrive to using Newton's laws of motion, just that here it will be much faster. So let's much more efficient. So let's take problem number 1. So we have the upward machine. So this is a standard example which shows acceleration, the constant acceleration. So it's a standard pulley problem. So you have a pulley which is massless, and you have two massless strings which are connecting masses m, small m, and capital M. And the question is, what is the acceleration of the system, or what is the force balance or equation of motion in the system? So usually in this problem, we take the string to be of length L, and here we take this position to be x, and this to be L minus x. So there is some listing here which you can add it to L and subtract it again later. So this is x and L minus x, and we have to construct a Lagrangian for the system. So the kinetic energy for the system, which is what we call as T, is nothing but you have, let's call beside our axis, so we have x and y directions. So this is nothing but half m. So this is along the minus y direction, and the distance is x. So it's minus x dot square, and similarly we have half capital M L minus x. So d by dt L minus x square. So it's again minus sign here because it's minus the negative y direction. So this is nothing but half m x dot square is half capital M x dot square. Since L is constant in time, so this is nothing but half small m is capital M times x dot square. So this is the kinetic energy in the system. Next is the potential energy. Which is nothing but capital V. So for such problems, we take the potential at a reference point to be 0, and we calculate what is the potential energy with respect to this point. So here this mass is at a distance x in the negative y direction, so we have minus mg x. The capital M, the mass capital M is at a position L minus x. So this gives minus mgl, and we get gx times capital M minus small. So this is the potential energy, and now what we have to do is to construct the Lagrange. This is T minus V. So we get half m plus capital M times x dot square, and then you get minus of this, so it's plus mgl, and we get minus of this, and that is, so we can take a minus out and then make it small m minus capital M times gx. So this is the Lagrangian for the system. So once we have the Lagrangian for the system, we can say that we can use the principle of least action, where we construct an action which is an integral of the Lagrangian over a time interval, and then we try to minimize this Lagrange or this action, and then we say that the system follows the path which minimizes this action interval. So that leads us to the Euler-Lagrange equation. So before that, we can look at this Lagrangian and simplify slightly by saying that you have a term which is a constant. So usually constant term in a Lagrangian will not affect the dynamics of the system. So for all purposes, we can remove this term. So here we have only one degree of freedom, one generalized coordinate. So the generalized coordinate here is x. L is a constant, so L is not figuring in any equation, is just x, which is the generalized coordinate. So now we apply the Lagrange equation or Euler-Lagrange equation, which is nothing but partial L over partial x minus d by dt partial L over partial x dot equal to 0. So once you have the expression for the Lagrangian, all you have to do is substitute it here, and what you get is for the partial L over partial x, you get a contribution from here, which gives small m minus capital M times g, and minus we have d by dt of partial L over partial x dot. So that is the contribution from here. So that gives you m plus m capital M times x dot, which should be equal to 0. So this equation is the Euler-Lagrange equation, which minimizes the action, and with that we get this equation. So I'll take the total time derivative. Here it's only with respect to x. So we get m plus capital M times x double dot is equal to small m minus capital M times g. Means the acceleration is nothing but small m minus capital M times g divided by small m plus capital. Okay. So if the masses are the same, we say that the acceleration is 0, and if the mass small m is greater than m, we have x double dot which is positive, and small m less than capital M, x double dot which is negative. Okay. So this is the standard results which you can also get using Newtonian mechanics, Newton's laws of motion. But here, this is an example where we say that by applying the Euler-Lagrange or Lagrange equation of motion, which is coming from the principle of least action, Hamilton's principle, which is called, we can get the same equation of motion as one gets from Newtonian mechanics. So this is a problem which takes roughly the same amount of time while doing for the Newtonian approach, when doing the Newtonian approach, and it takes about the same time when we do using Lagrangian mechanics. So next problem which we'll see, the next problem which we'll see, we will use the Lagrangian approach, but if one follows the Newtonian approach or Newtonian mechanics, one can easily see that the Newtonian approach, Newtonian mechanics will take much longer time to solve the problem. So that brings us to problem number 2. Like P. So problem 2. So this is a very standard problem known as the double pendulum. So here you have two masses, m1 and m2, which are attached from a support. So m1, you have m2. Here you have L1 and L2, which are the length of the rods, which are attached from the support. And the question is to write down the equations of motion for the system. So M1 is free to rotate about this hinge point, and M2 is free to rotate about the hinge, which is the M1 point. M2 can freely rotate about M1. So in real life situations, if one has to construct such double pendulums, what one does is to make some kind of a rod and then attach another rod slightly displaced, slightly out of phase, and then you give another mass. So this is mass m1, this is mass m2, and because the hinge is slightly separate, this mass can rotate about m1, and m1 can also rotate about the hinge. So this is the standard double pendulum. So let's go to the question. Consider the problem of double pendulum as shown below. Take the masses to be m1 and m2 and the lengths to be l1 and l2. So first, you have to write down the governing equations in terms of the Cartesian coordinates. So this is the part which is an exercise is to find the equations of motion in Newtonian mechanics. So here we don't consider the Lagrangian, which is part B. So this part A, one has to do it using the standard Newtonian approach, and soon it will be clear that it will take much longer time as compared to the Lagrangian mechanics. And part B is write down the Lagrangian for the system using generalized coordinates and the resulting governing equations. So this is the part that I will try to concentrate upon here, and just read out. So we have one hinge here, and then you have one mass m1, and then you have another mass which is m2. So as one can see from here, the length of the rods, the massless rods, are fixed to be L1 and L2. And since the masses are fixed, the lengths are fixed, all m1 and m2 can do is just to rotate about their hinge. So the coordinate which describes the position of m1 is just theta1, and the coordinate which describes the position of m2 with respect to m1 is theta. So once you know theta1 and theta2, one can describe m1 and m2 with the position of both masses m1 and m2. So we have two generalized coordinates, theta1 and theta2. Now the question comes, how do you write the Lagrangian for this system? So let's construct an axis system. So let's say x and y direction we take along these directions, and once we have the generalized coordinates, we can write the position vector. So let's say r1 vector, which is the position vector of the mass m1. So this is nothing but, so along x direction it's L1 sine theta 1, and along y direction it's minus L1 cos theta. Similarly, one can do the same thing for the position vector of mass m2. So that is nothing but, since the position vector is given by x1, so this distance plus this distance, so you have L1 sine theta 1 plus L2 sine theta 2, and the y direction again one has to take these two lengths, so you get minus L1 cos theta 1 minus L2 cos theta. So this is the position vector for mass 2 and mass 1, and we'll start constructing the kinetic energy. So this will denote it as T. So this is nothing but half m r1 dot square plus, so half m1 r1 dot square plus half m2 r2 dot square. So we can write r1 dot is nothing but, so we take the time derivative of this term, so we get L1 cos theta 1 times theta 1 dot. And when we take time derivative here, we get L1 sin theta 1 times theta 1 dot. So this implies R1 vector dot square is nothing but this component square plus this component square. So one gets L1 square cos theta 1 square times theta 1 dot square plus L1 square sin square sin cos square theta 1. And this is L1 square sin square theta 1 times theta 1 dot square. So that is nothing but, we can take L1 square theta 1 dot square times cos square theta 1 plus sin square theta 1, which is 1. So this is nothing but L1 square theta 1 dot square. Okay, and the next one is R2 dot, nothing but, again you can take derivatives here. So we take derivatives of R2 and we get cos theta L1 cos theta 1 dot plus L2 cos theta 2 dot, and you get L1 sin theta 1 dot plus L2 sin theta 2 dot. And we can try to construct L2 dot square, nothing but L1 square cos square theta 1 dot square plus L2 square cos square theta 2 dot square plus 2L1 into cos theta 1 cos theta 2 theta 1 dot theta 2. So this is nothing but this square, the first component square, and then you get L2 square sin square theta 1 dot square plus L2 square sin square theta 2. So this is L1 sin square theta 1, L2 square sin square, L1 square sin square theta 1 dot square, L2 square sin square theta 2 dot square plus 2L1 L2 sin theta 1 sin theta 2 times theta 1 dot theta 2. So I'll take it over to the next page. So you get R2 dot square, nothing but. So these two terms we can combine. Similarly, these two terms we can combine. So we get cos square theta 1 sin square theta 1 cos square theta 2 sin square theta 2. That gives you L1 square theta 1 dot square plus L2 square theta 2 dot. The final term you can also combine, and one gets cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. That is nothing but cos of theta 1 minus theta 2. So one gets plus 2 L1 L2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2. So the kinetic energy T is nothing but half m1 L1 square theta 1 dot square plus half m2 L1 square theta 1 dot square plus L2 square theta 2 dot square plus 2 L1 L2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2. Okay, so we can see that these two terms we can combine and we get half of m1 plus m2 L1 square theta 1 dot square plus half M2 L2 square theta 2 dot square plus 2 L1 into theta 1 dot theta 2 dot cos of theta 1 minus theta 2. So this is the kinetic energy, and next is the potential energy. So this is simple. One has to just define a zero. So we call this as a reference for zero. So we have one which is at a distance minus L1 cos theta 1. The other one with respect to the first one is minus L2 cos theta 2. So that gives you V equal to minus M1 G L1 cos theta 1 minus M2 G times L1 cos theta 1 plus L2 cos theta. So this basically comes from minus mgn. So since g y is given by these two terms, so we have one which comes from m1, so we get minus mg l1 cos theta 1. The other one is minus mg m. First one is minus m1g l1 cos theta 1. Second one is minus m2g times l1 cos theta 1 plus l2 cos theta. That is exactly what I wrote here. And again, we can write this as minus m1 plus m2 and g l1 cos theta 1 minus m2 g l2 cos theta 2. So this is the expression for the potential energy. And the Lagrangian is nothing but T minus V, and we write it as half m1 plus m2 l1 square theta 1 dot square plus half m2 L2 square theta 2 dot square plus 2 L1 L2 theta 1 dot theta 2 dot cos of theta 1 minus theta 2. So it's minus of V, so we get plus M1 plus M2 times G L1 cos theta 1 plus M2 G L2 cos theta 2. So this is the expression for the Lagrangian. So we took some time to write down the kinetic energy in terms of position r vector and found the velocity vector, and then took v square, found the kinetic energy for both the mass m1 and m2. So once we have the kinetic energy and the potential energy, we can write down the Lagrangian. This is what is written. To arrive at the same result, the Newtonian system would take slightly longer time to get to the equations of motion. Here, once we have the Lagrangian, the equations of motion are much more simpler, which comes from the principle of least action, or the Lagrange's equation of motion. And what we get from that is that, so since we have two generalized coordinates, we can do minimization over these two coordinates, and we get two equations of motion. So you have theta 1 and theta 2. So you get the two equations for theta 1 for these two angles. So first equation is in terms of theta 1. So we have partial L over partial theta 1 minus d by dt partial L over partial theta 1 dot equal to 0. So let's do this step by step so that we don't make any errors. So let's first find out what is partial L over partial theta 1. So partial L over partial theta 1, we see that we should get an expression from this term because it has theta 1 here. We should get an expression from here, and that's it. There are only two terms which gives us theta 1. The first one we get half m2 times 2 L1 L2 theta 1 dot theta 2 dot. So we can write this as partial cos by partial theta 1, so that is minus sign, theta 1 minus theta 2, and then we just take partial of theta 1 minus theta 2 by partial theta 2, that is theta 1, which is 1. So you get minus sign of theta 1 minus theta 2. So this from this term, and the other term which gives us minus m1 plus m2 gl1 sine theta 1. So this is just differentiating cos theta 1 with respect to theta 1. Next up, we have, so I'll just move this a bit. Center. Next up, we want to find what is partial L over partial theta 1 dot. So we'll follow the same procedure. So we'll identify the terms which gives us the contribution for partial L over partial theta. So we have one contribution from here, one contribution from here, and that's it. For the first one, we get m1 plus m2 L1 square theta 1 dot. So this is taking derivative of this term, and then we have derivative of that term, which is m2 L1 L2 theta 2 dot cos of theta 1 minus theta. So once we have this, we'll find d by dt of partial L over partial theta 1 dot. So this is nothing but m1 plus m2. So we are taking the total derivative here. So for the first term, only theta 1 is a function of time. So we are taking total derivative. This is a constant, this is a constant. So only theta 1 you have to take time derivative. Theta 1 dot you have to take time derivative. So that gives you theta 1 double dot. Plus here, one should be careful. Here both these terms depend on time. So when you take the total time derivative, one should make sure that we take time derivative with respect to this term, the first term, and time derivative with respect to the second term. This is a common place of error which people should avoid. So one should make sure that one takes the total time derivative with respect to both the terms which are present. So that gives you m2 L1 L2. So first we get theta 2 double dot cos of theta 1 minus theta 2, and the other term which one gets is theta 2 dot times minus sine of theta 1 minus theta 2 times theta 1 dot minus theta 2. So that we can expand. So that gives us m1 plus m2 theta 1 double dot. So this one, first term is m2 L1 L2 theta 2 double dot cos of theta 1 minus theta 2. And here we get minus m2 L1 L2 sine of theta 1 minus theta 2 times theta 2 dot times theta 1 dot minus theta 2. So now all we have to do is equate these two terms to get the equation of motion. From here we see that we have to equate this term and this term. That gives us the equation of motion. So I'll make it into the next page. So we'll write it as we have one term which is m1 plus m2 and theta 1 dot double dot. That should be, so here there is an L1 square which is missing. L1 square. So what I'll do is copy this. So it's m1 plus m2 times theta 1 double dot, and one gets plus m2 L1 L2 theta 2 double dot cos of theta 1 minus theta 2 minus m2 L1 L2 theta 2 double dot theta 2 dot times sine of theta 1 minus theta 2 times theta 1 dot minus theta 2 dot. Okay, so this is the term which comes from d by dt, and this should be equal to the term here. So again, I will do the same trick. Let's copy this. Put it here. So this should be equal to m2 L1 L2 theta 1 dot, there's a minus here, plus a minus here, theta 1 dot theta 2 dot sine of theta 1 minus theta 2 minus m1 plus m2 times g L1 sine theta. So this is your first equation. So this is the equation for theta 1, but we see that we have both theta 1 and theta 2 in this equation, which means that dynamics of both the equations are coupled. So this is normal because the moment of m1 is also coupled to the moment of m2. So these two masses can exchange their potential of kinetic energy. So that is why we have these cross terms, and just simplify this term to get the final equation. So one can see that, for example, this term is the same as the term which comes out from this term. So we have theta 1 dot times m2 L1 L2 theta 2 dot sine theta 1 minus theta 2, which is the same as the term which is on the right hand side. So we can cancel out these two terms, and the resulting equation nothing but m1 plus m2 theta 1 double dot plus m2 L1 L2 theta 2 double dot cos of theta 1 minus theta 2. So we get minus times minus is plus m2 L1 L2 theta 2 dot square times sine theta 1 minus theta 2, and I take this term to the left hand side, you get m1 plus m2 times g L1 sine theta 1 equal to 0. And we can do, so there's one more issue here, there is an L1 square which is this. A good check when one derives such equations is dimensional analysis. So once one derives such an equation, a quick check would be take to find the dimensions of each and every. For example, the first term, we see that it's mass times m times L over t square. So theta does not have dimensions, it's just the angle. So theta double dot has dimensions 1 over t square, L has a dimension L, so it's actually L square, and this is mass. So it's ml square over t square. So one has to verify that each and every term has the same dimension, and if there's a discrepancy, it means that there is an error symbol. So here we find that all these terms have ml square over t square dimension. So at least dimensionally, one does not have an error in this equation. So we can do one more simplification. We can divide by L1 because L1 is a common factor everywhere, and that gives you the final equation m1 plus m2 L1 theta 1 double dot plus m2 L2 theta 2 double dot cos of theta 1 minus theta 2 plus m2 L2 theta 2 dot square sine of theta 1 minus theta 2 plus m1 plus m2 times g sin theta 1 equal to 0. Okay. So we can also verify that if we put m2 or L2 to be m2 and L2 to be 0, we get back the standard simple pendulum, which can be verified easily, and you can verify yourself that is indeed what you get. So now let's look at the second equation for theta. So it's the same procedure. So it's partial L over partial theta 2 minus d by dt partial L over partial theta 2 dot equal to 0. The same procedure, and what one has to do is to find first partial L over partial theta 2 is nothing but, so I'll just copy the Lagrangian. So what I can do it here. So here one gets, so this is Lagrangian, so one gets this part. So one gets one term for theta 2. There's one term which comes from here, one term which comes from here. So that you can write it as m2 L1 L2 theta 1 dot theta 2 dot. So it's, you're taking derivative of cos of theta 1 minus theta 2, that gives you minus sine of theta 1 minus theta 2, and then one has to take partial derivative with respect to theta 2 of theta 1 minus theta 2, which is minus 1. So this is the contribution from the first term. We have another contribution from this term, which is nothing but minus m2 g L2 sine of theta 2. Now let's go to partial L over partial theta 2 dot. So here one has to look at the contributions from this term, the theta 2 dot. It's a partial over partial theta 2 dot. We have a contribution from here, and that's it. Two contributions. So first one gives you m2 L2 square theta 2 dot, and the other one is m2 L1 L2 theta 1 dot cos of theta 1 minus theta. So I think our need for Lagrangian is no longer needed, so I'll just erase this out. So now we have to find the total time derivative of partial L over partial theta 2 dot. So this is nothing but m2 L2 square, which are constants, theta 2 dot, take partial total time derivative again, get theta 2 double, and we get m2 L1 L2. So you get one. So when you take the total time derivative of this term, one has to make sure that you take time derivative with respect to theta 1 dot and the cost term. So that gives us theta 1 double dot cost of theta 1 minus theta 2, and the other term is minus theta 1 dot sine of theta 1 minus theta 2 times theta 1 dot minus theta 2. So this is nothing but m2 L2 square theta 2 double dot plus m2 L1 L2 times theta 1 double dot cos of theta 1 minus theta 2. So the first term is nothing but theta 1 dot square sine of theta 1 minus theta 2. Second term is plus theta 1 dot theta 2 dot sine of theta 1 minus theta 2. So now all one has to do is to equate these two terms. Try to do it here itself. So one gets m2 L2 theta 2 double dot plus m2 L1 L2 theta 1 double dot cos of theta 1 minus theta 2, and then one gets minus m2 L1 L2 theta 1 dot square sine of theta 1 minus theta 2 plus m2 L1 L2 theta 1 dot theta 2 dot sine of theta 1 minus theta 2. So this should be equal to the term above. So the first term has double minus, so it's a plus. So one gets m2 L1 L2 theta 1 dot theta 2 dot square theta 2 dot sine of theta 1 minus theta 2. And the last term, which is minus mg L2 sine of theta 2. Okay. So again we can simplify here. So first is to notice that these two terms are the same. So we can remove these two terms. So I'll take the calculation over to the next page. So from here we get m m2 L2 square theta 2 double dot plus m2 L1 L2 theta 1 double dot cos of theta 1 minus theta 2 minus m2 L1 L2 theta 1 dot square sine of theta 1 minus theta 2. So we can take this to the left hand side. So then you get minus m2g L2 sine of theta 2 equal to 0. So again you can notice that dimensions of all the terms should be the same. So here you get mass times L over L square over T square, mass times L square over T square, mass times L square over T square, mass times L over T square times L, which is the same with all the other terms. So this is a nice check to just verify that we are doing all right. And now we can divide this one simplification, we can divide by m2 n2. So this gives us n. So since n2 is common everywhere, we can take it out. So this gives us L2 theta 2 dot double dot plus L1 theta 1 double dot cos of theta 1 minus theta 2 minus L1 theta 1 dot square sine of theta 1 minus theta 2 plus g sine theta 2 equal to 0. So this is our second equation of motion. So we get two equations of motion, one for theta 1, another one for theta 2, and they are both coupled. So this is a coupled system of equations, and if one analyzes further, one sees that this is a coupled highly nonlinear system of equations, and this is one of the typical examples which shows that a system which is highly nonlinear, like these equations, can become chaotic. So if one has a physical example of a double pendulum, so we have one mass, another mass, and if one gives sufficiently enough energy, the double pendulum will start moving in a very chaotic fashion. When I say chaotic fashion, it means that after a few instants of time, it will become harder and harder to predict its position. So you need a lot of accuracy, or one should exactly know the equations and integrate it in time exactly to get to predict the position. Otherwise, what one observes is a very, or what happens is that prediction of the position becomes harder. So this goes into what is known as chaos theory and highly nonlinear systems, or dynamic systems, and this is a separate course in itself. So we'll just stop here with respect to equations of motion. So there's one particular thing which people can do with this system is to linearize and get a solution the limit of small oscillations. So this is the final part of this exercise. Maybe it's not a bad idea. So taking M1 and M2 to be M1 equal to M2 and L1 equal to L2, solve the governing equations in the limit of small oscillations. So here what we say is that when we say small oscillations, so theta 1 is very much less than 1, theta 2 is very much less than 1, meaning that the oscillations of the pendulum are very close to 0. So if we do not push it very far from the position which is at rest, so we don't push the pendulum too far, so the initial energy is very small and the system is oscillating with not much amplitude. So we can make some approximations saying that cos theta 1 minus theta 2 is almost 1, sine of theta 1 minus theta 2 is equal to theta 1 plus minus theta 2 plus some approximation. This is an approximate term, and sine theta 1 is approximately theta 1, sine theta 2 is approximately theta 2, and cos theta 1 is approximately 1, cos theta 2 is approximately 1. So with these assumptions, or with this in the limit of small oscillations, one can exactly look at some solutions for this problem. So I'll again copy this equation, since we will do this. We will try to get some solution from this system. So this is the first equation. So when we do this small oscillation of limit, small oscillation gives, so we get m1 plus m2 times L1 theta 1 double dot. So in the second term we get m2 L2 theta 2 double dot. Cos of theta 1 minus theta 2 is approximately theta 1 minus theta 2. And the third term is theta 2 dot square and sine theta 1 minus theta 2. So this is of the order of theta cube. So this is typically a small parameter, so we'll neglect this, plus m1 plus m2 times g theta 1 equal to 0. So this is the typical thing which one does for a small pendulum, so a simple pendulum. One says that sine theta 1, even though sine theta 1 has theta 1 minus theta cube by 3 and terms like that, we just take the first order expansion. So we just take sine theta equal to theta. And so this is the first equation, and the second equation is so that gives us L2 theta 2 double dot. So again here you can say cos theta 1 minus theta 2 is approximately equal to 1. So it's one gets L1 theta 1 double dot. And here again we have theta cube, order theta cube, which you can neglect, and one gets g theta 2 equal to 0. So I'll just remove these two terms, these two equations. We say small oscillations. These are the two governing equations in the limit of small oscillations. So these two equations are, so effectively what we did is that we have linearized the system, and there's one more assumption which was given in the question is to take m1 equal to m2 and l1 equal to l2. So we can also do that. We get 2m l1 theta 1 double dot. So there's no longer l1, there's no longer l1 l2, so just 2 and L theta 1 double dot plus M L theta 2 double dot plus 2 and G theta 1 equal to 0, and the other one is L theta 2 double dot plus L theta 1 double dot plus G theta 2 equal to 0. So we can remove M from the first equation. So now we have a system of equations which is in terms of just theta 1 and theta 2. And since it's a linear system of equation, so just rearranging it, we can look at solutions for this linear system of equations, which are of the form theta 1 is equal to e power I omega t, a1 e power I omega t, and theta 2 should be equal to a2 e power I omega t. So one can substitute such equations. So here what one gets is minus omega square 2a1 plus a2 equal to minus 2g over L a1, and the second equation one gets minus omega square a1 plus a2 equal to minus g over L a2. So we are basically trying to find what are the solutions in the limit of small oscillations. So you get sinusoidal or periodic solutions, exponential I omega t. This is exactly what one gets if you are looking at simple pendulum problems, or the standard pendulum problem, where in the limit of small oscillation you get nice periodic motion, and even for a double pendulum, even though the frequencies are slightly different, as we will see, we do get nice sinusoidal motions. So this is a system of equation for a1 and a2, and since a1 and a2 are not equal to 0, we can say the determinant is 0. So we get, so I'll try to rearrange it. We can write it as 2g over L minus omega square a1 plus minus omega square a2 equal to 0, and the other is minus omega square a1 plus g over L minus omega square a2 equal to 0. So taking the determinant of this matrix, gives us the eigenvalues for the system. So this gives minus omega power 4 equal to 0. So this is nothing but omega power 4, and one gets minus omega power 4 plus 2g over L and g over L minus omega square 2g over L plus g over L equal to 0. So this is nothing but this equation. We are simplifying this to get the frequency which is chosen by this oscillator. So these two terms one can take away, so one gets omega square equal to maybe it is possible. Yes, there's a mistake somewhere. There's a minus 2 here. There's a minus 2 here. And did I make any other mistake? No, okay, it is fine. So yes, one should be careful. So this is not exactly 0. So one gets 2 omega power 4 minus omega power 4. So one of it gets cancelled. So one gets omega square, omega power 4 minus, so one gets plus 2g square over L square. So just to verify that there's no error in it,